separating a liquid and a gas creates a higher pressure in the concave side as compared to that in the convex sides. This is one phenomenon observed. Now let us see this thing here. Let us see here. This is a curved, elemental curved liquid surface which distinguishes or separates the bulk of the liquid on its concave side. That means this side is the bulk of the liquid and this is the convex side, this side is the air. For example, air or any immiscible fluid, any gas. So this is a small curved elemental liquid surface. Now let us see that the surface is curved in both the directions in such a way that the radius of curvature in this direction is R2, which is less, that means it is more curved, and in another direction is R1. And the lengths of the curved surfaces are such that they subtend angles of d theta 2, that means this is d theta 2, this angle is d theta 2, this is d theta 2, and this is d theta 1, this is d theta 1, this angle, d theta 1 and d theta 2 at the respective center of curvature. These are the respective center of curvature. This is R1, this is R2. This is curved in both the directions, elemental curved surface. So this side, that means the convex side, this is gas, and in the concave side is the bulk of the liquid. We only consider a small elemental curved portion of the surface. Now you see the surface tension force acts on these four sides. Now these two sides which are of radius of curvature R2, the surface tension force acts perpendicular to this linear element, you see, whose lengths are R2 d theta 2. Therefore this force is sigma R2 d theta 2, which is written here, I think you can see. So this is the surface tension force acting, which is perpendicular to this curved element, and it is sigma R2 d theta 2. R2 d theta 2 is the length of this element. Similarly, the surface tension force which acts over these elements, these lengths, this is sigma R1 d theta 1, because the length of this curved line is the R1 d theta 1. So according to the definition of surface tension, the total force is sigma R1 d theta 1 in this direction. Now if we look, this is a three-dimensional view. If you look two-dimensional view, that means if you look from this angle, therefore we see only this part of the curve like this, where these forces acting on like this. I am showing it by only one arrow, so this is acting like this. So this is sigma into R2 d theta 2. All the forces sum up with this sigma into R2 d theta 2. So this will appear like that, sigma into R2 d theta 2. So this is d theta 1, that means you see this view. Well, so from very simple geometry you see this is d theta 1. So this angle will be d theta 1 by 2, these angles. Why? This is because this angle will be, this is 90 degree, because this is tangent, this direction. So this and this radius of curvature will be perpendicular, so these angles are 90 degree. So that this is 180 degree minus d theta 1. So therefore, these angles will be d theta 1 by 2. Similarly, if we see a view from this direction, we will see the forces are acting, which are the forces? These forces. So if you see this view, these forces are acting sigma R1 d theta 1, sigma R1 d theta 1. And these angles are d theta 2 by 2, because this is d theta 2 from simple geometry. This angle, this is d theta 2 by 2, this is d theta 2 by 2. So if you can recognize this, then a simple force balance, now let us write, assuming that the convex side of this liquid surface is acted on by an uniform pressure P0, that is the pressure of the gas which demarcates this liquid. Similarly, the interior of the liquid, the pressure is Pi, which is acting perpendicular to these surfaces, that means in its concave side, let this is Pi. Now therefore, if we make a force balance in the vertical direction, then we get the surface tension forces acting sigma R2 d theta 2 in two surfaces. So 2 sigma R2 d theta 2 into sine d theta 1 by 2. sine component. This is d theta 1 by 2 vertical direction. Similarly, the force component due to sigma r1 d theta 1 on both the sides, that means this side and this side, which is shown like this, is twice sigma r1 d theta 1 sine, well, d theta 2 by 2. And this net force in the downward direction will be balanced by the net pressure force in the upward direction. That means Pi minus P0 times the surface area over which the difference of pressure. That means each and individual pressure is acting over a surface area. So pressure force is the pressure times the surface area. So similarly, Pi into surface area minus P0 into surface area, Pi minus P0 into surface area, which is the product of these two lengths. That means R1 d theta 1 into R2 d theta 2. Now with a simple relationship from trigonometry, that for small angles, because this is a small elemental curved surface where the sides subtend small angles d theta 1 and d theta 2 at the respective centers of curvature, we can write that for small angles the sine of the angle is equal to the angle. If you see this series, the series for sine function, you will see we can neglect the higher order terms, so you can approximately write d theta 1 by 2. So you know this thing that sine theta is theta. Similarly, d theta 2 is equal to d theta 2 because the higher order term in this series can be neglected. So if we now substitute this in terms in place of sine, that means in place of sine d theta 1 by 2, I substitute d theta 1 by 2, and in place of sine d theta 2 by 2, I substitute d theta 2 by 2, and then by simple simplification, I get this Pi minus P0 into R1 R2 d theta 1 d theta 2 is equal to what we get, sigma R2 d theta 1 d theta 2 plus sigma R2 into what? This is sigma R1 into d theta 1 d theta 2. So ultimately, if I replace this as delta P, define Pi minus P0, we get sigma into 1 by R1 plus 1 by R2. So this is a very, very important formula. Now therefore we see that there is the difference in pressure created. That means the concave side is having a higher pressure Pi than the convex side, where the gas is there and concave side is the bulk of the liquid, and this difference of pressure is given by the surface tension coefficient and the radius of curvature of the two sides. This is the general case of a liquid surface, liquid interface which is curved in both directions.